Okay, good afternoon. So firstly, thank you for the invitation to speak today. I've been a previous attendee of the forum, and it's with great pleasure I'm here today representing the Hexagon and NovAtel team. I'm James Szabo, the Agriculture and Autonomy Product Manager based in the UK, driving the autonomy efforts within NovAtel to be able to provide relevant and successful products for our industry partners. So to start with a bit of background on the company, Hexagon is globally known for its positioning and measurement technologies in multiple industries from construction, military, marine, aviation, and of course agriculture, with over 20,000 employees globally. We focus on providing high quality positioning and measuring in the most demanding environments and scenarios. Under the Hexagon Group name, there are many subsidiaries which are well known within ag, such as Leica, Hexagon Agriculture, NovAtel, and TerraStar Correction Services. Today, within agriculture, many guidance solutions and auto steer systems are built on the same technology and infrastructure, which over the years have matured in both availability and reliability. However, they all have the same fundamental limitations, which can cause frustrations for its users and will ultimately inhibit higher levels of automation. Anyone who has operated a tractor with auto steer or precision farming equipment relying on GNSS will have had an experience at some point in time of a position dropout. In autonomy, in order to be safe, efficient, and reliable, we need to move away from the good enough approach and focus on how we can calculate the vehicle's position with a higher level of accuracy, precision, and integrity. As the production and scale of autonomous machines grow, as an industry, we have the responsibility to avoid and mitigate future risks, thus preventing scenarios like the one shown in the picture here when in autonomous operation. If we take a high-level view of the GNSS and vehicle control structure, in the majority of agricultural vehicles today, they're all formed of a similar architecture. First, we have a GNSS receiver, some IMUs on the vehicle, and a vehicle controller. And then externally to the vehicle, some form of GNSS constellation, whether that's the American GPS, Russian GLONASS, Baidu, Galileo. And finally, we have some form of correction source. And this might be a local RTK station with transmission over radio or VRS network transmitted over cellular, or even satellite delivered corrections. In a manned solution, these systems operate usually very, very well in the majority of scenarios. And as we fall back to level one, the ability to fall back to level one automation is always there. Basically, an operator can take control of the vehicle at any point to resume the operation. But for automation, we need to achieve a position that is more than just there the majority of the time. Any interaction an operator has with the vehicle is essentially a failure of automation. So by far, the most common failure of classic GNSS position is the lack of availability or view of satellites. Objects such as pylons, trees, buildings can all have a negative impact on the calculated position. This severity might be from a few centimeter deviation up to a complete and full position loss. The view of satellites is compromised by physical block or manipulation of the signals, thus something very hard to mitigate. A single receiver on its own cannot verify its position, and it's also very vulnerable to jamming and spoofing of positions, which unfortunately is an increasing global risk. For higher accuracy operations, there's a reliance on a correction service. This needs to be delivered somehow to the vehicle. This communication channel, whether it's UHF, L-band satellite, or cellular, is passing through a lot of infrastructure which is vulnerable to failure, even before reaching the vehicle. Furthermore, the correction sources and accuracy and integrity can be very easily compromised, especially at end user installed solutions such as mobile base stations, farmer installed networks. But then you also have the limitations of the baselines of approximately 40 kilometers. And the further you get away from the base, the further you have a degradation of your accuracy. So the lack of consistency in the solution leads to risks of objects and obstacles, field boundaries, and logistics points that are being mapped having correction source mismatches. How do you know the correction source used to survey a field is the same correction source as the vehicle that's going to be operating in the field? And finally, again, single receiver on a vehicle brings potential ambiguation of the heading, especially at low speeds or when we're static. Compasses and gyros are exceptionally good when movement is occurring on the vehicle. However, from cold starts or after being idle for a length of time, this heading can actually be compromised. Look into the future when we aspire for vehicles to be operating at level 4 automation and above. We want the operations to be smart. We want the vehicle to be stopping for weather. We want it to be stopping for obstacles. We want it to be stopping for ideal spray conditions. So the vehicle needs to be able to effectively and safely resume at an operation. And these small factors are essential for the customer to receive the best possible experience of his product. Okay, so overall, there are multiple potential points of failure and multiple points of potential ambiguation, which leads to the classic GNSS approach not really being good enough to solely rely upon for positioning in autonomy. So these limitations have been identified by our customers, and it's been driving ourselves to build products and solutions which can help mitigate the scenarios and problems that I've highlighted. So let's talk about some of the ways that we've overcome these problems. Well, first, we need to recognize what is our aim, what is our requirement for position in autonomy. From a positioning standpoint, we can break the requirements down into two main signal goals. First is the task position. This is the accuracy that we need in order to achieve our task, whether it's seeding, disking, harvest, or any other operation. Today, we're used up to 2.5 centimeter accuracy, and that's deemed ideal for nearly all operations. However, the position is statistically only accurate 95% of the time. And this is not reliable enough for full automation. And a result of the combination of the factors that I've listed before and some others means it cannot solely be relied upon. The second position is what we call the safe position. And this is an assured position, which ensures up to the 5 nines that the position is accurate. Now, this means 99.999% of the time, we can assure that that position is within the accuracy that was stated. So based on the application and scenario, the aim is to keep the position output, or the HPL, under a safe zone or a threshold, with an integrity higher than the safety requirement of the system. And only when this criteria has been met that you can provide a assured position for 99.999% of the time. So from the Hexagon and TerraStar perspective, there are several ways in which we're building up the confidence, integrity, and availability of our solutions in order to move away from the classic good enough towards assured positioning. One key part of the solution is ensuring that the corrections or the correction services used can be consistent across the entire fleet of vehicles and data providers that might be involved in the operation of the autonomous system. The TerraStar service can provide an automotive safety and integrity level required for the customer's particular requirements. Across the entire chain of the solution, redundancy and risk mitigation has taken place to make sure that we can help our partners achieve their functional safety goals. These services are available globally, thus removing the requirement and reliance on local infrastructure or even mobile base stations as part of the solution. Solving the problem of heading and position integrity, multiple receivers can actually be paired with each other, which can give higher levels of position confidence as well as static heading from initialization without the need for an operator to move the vehicle or calibrate like would be with a single GNSS with IMUs. The align function today already exists and it's within our receivers firmware, and it provides a quick way of pairing two receivers for the reliable heading, or allowing multiple receivers on multiple rovers working together in proximity, which is ideal for a leader-follower type scenario or implement guidance. That way you can get a reliable relative position between multiple points in a field. Furthermore, depending on the use case, it's possible to bring extra sense information into the positioning engine. This might take the form of gyroscopes, which we have already added with our span technology, which tightly couples the GNSS with the inertials for continuous operation through poor satellite availability. And for the autonomy operations, this is being extended further and improved upon further with the integration of visual odometry, utilizing our scene and environmental perception cameras, as well as physical sensors such as wheel angles and impulse sensors. So only when multiple positions created by GNSS, visual odometry, IMUs, sensors, when they are merged and fused together, can the true vehicle position be actually understood with the higher level of integrity that is required for reliable autonomous operation, thus separating and distinguishing positioning solutions required for autonomy against positioning solutions traditionally used. So, to summarize, to help our partners in 2020, NovAtel launched its positioning and autonomy kits to aid with platform developments. Our kits are modular to meet with your requirements and to help solve particular problems. So first we have the GNSS kits, which provides such modules such as the absolute heading with the Align software, with the sensor fusion and the span technology, and access to the TerraStar correction services. Secondly, for those requiring sensor hardware, using the expertise from our autonomous stuff division, we have a range of sensors including radar, LiDAR, RGB cameras, stereo cameras, and the supporting hardware to enable obstacle detection, obstacle classification, and simultaneous location and mapping, or SLAM. And finally, we offer development services to assist our partners achieve their requirement goals. And this can reduce time to market as well as provide a more robust positioning and perception solution. So thank you very much for your attention today. If you have any questions or comments or feedback on anything I've discussed today, please do come along to the virtual booth. Myself and colleagues will be there to answer your questions. And we do have some time now for the Q&A, so I'm going to stop the screen share and have a look, see if we have any questions. Okay, we have a question here. You were talking about bad satellite visibility under trees in thick foliage. What is the drift over distance in quantitative terms that you can expect from your span and GNSS INS in these situations? Okay, that's quite a difficult one to answer in quantitative terms. If possible, could you come over to the booth afterwards? In fact, I'll scribble down the name and we can provide some detailed statistical information for you on that for that question. Can SLAM be fused using SPAN? Again, this is a very technical question. Multiple technologies can be used with the SPAN engine. So I think we need to speak about your specific requirements and whether we can solve them with the SPAN solution. Do you provide any of these technologies for navigation inside greenhouses? Yes, we do have some relative navigation technologies utilizing visual odometry. Again, please do come along to the booth and we can talk about your specific requirements in there. Okay, I think we have some questions in the chat. Nope. Okay. So a question again, really targeting autonomous stuff. Tanner looks to be answering that question now. I'll leave that to him.
I think you can answer the question.
Okay, so the question is autonomous stuff question. Are autonomous stuff now providing object detection components? So the answer to that is yes. There are multiple technologies, including camera, radar, LiDAR, which can be used to detect and classify objects depending, again, on the requirements of your system. To clarify, software components. So the software itself is not released as a standalone product. What we would be talking about is more focusing on how they can advise and help you build your software component out. But again, it's quite a specific question, so please do come onto the booth and we can go into it in more detail. Okay, if there's no more questions, then I welcome you to come to the booth and then we can discuss further. Thank you.